Hi, my name is Tonia Mielke. I'm from the University of Magdeburg, and I want to present you our work, SensARy Substitution, Augmented Reality Techniques to Enhance Force Perception in Touchless Robot Control. So first we come to our motivation. In human-robot collaboration, automatic and interactive control methods are combined. Therefore, the robot can be controlled through different interaction methods, for example, using joysticks or hand gestures. This interaction can enable intuitive control and allow adaptability to dynamic work environments. However, this leads to a loss in direct force perception, which is important for industrial tasks such as polishing or medical robotic applications. Another example where the contact force between the robotic end effector and the environment is crucial is robotic ultrasound. Here, an ultrasound probe is attached to the robot, and a consistent force is important for imaging repeatability and patient safety. Now I want to give an overview over the related work and the research gap. So firstly, SensARy substitution modalities. So onto which modality can we map the force perception if direct force perception is missing? There have been investigations on primary visual, vibrotactile, and auditive feedback. However, these works primarily focus on robotic surgery or industrial tasks, but there is only limited work for robotic ultrasound. The main area that is investigated is visual feedback. So here different visualization concepts were explored, and it was found that redundant cues such as color and shape changes are beneficial. However, there was no comparison yet of the two prevalent methods, namely a bar and an arrow. And then we have the visualization placements. Through AR, we can place the feedback at different positions. And the related work has explored robot, world, or body stabilized placements. However, these different placements have not been compared yet for different force visualizations. This brings us to our research questions. First, which modality is best suited to convey force information? Second, how should visual feedback be designed? And third, where should visual feedback be placed for optimal perception? To address these questions, we explored vibrotactile and visual feedback, as audio feedback has been shown to be unsuitable in the medical context. For the vibrotactile feedback, we used pulsed vibrations with different patterns to depict a force above or below the goal force. And we had an increased frequency when approaching the target force. Then we had two visualizations, where the first one was a 2D bar, where the height changes were proportional to the applied force, and discrete colors indicated the relative force. And the second visualization is a 3D arrow, where the arrow size and continuous colors represented the relative force, and additionally, the arrow's pointing direction also showed the force direction. For placement, we explored three positions. The first is anchored to the world, namely on the screen displaying the ultrasound image. The second is at the robotic end effector overlying the ultrasound probe. The last placement is body stabilized, showing the feedback anchored within the user's field of view. We implemented our prototype using a Microsoft HoloLens 2, the KUKA LBR EVA robotic arm, the vibrotactile lock-lid bracelet, and a Clarius ultrasound probe, which was attached to the robotic arm using a 3D printed mount. For the robot control, we used a touchless interaction technique, which was based on mid-air hand gestures. Therefore, a virtual probe was displayed in the user's hand, and its relative movements were mapped onto the robot motion. The registration between the robot and the HoloLens was conducted using a pivot-calibrated image marker for point-based registration. To evaluate the different modalities, designs, and placement, we conducted a within-subject user study with 21 participants. The task was to control the robot for ultrasound imaging, where participants had to locate different geometric shapes embedded in a phantom. To assess performance and subjective preference, we measured task completion time, force deviation, average maximum force, perceived difficulty, and perceived continuity. Here you can see our study setup. So where, for example, the ultrasound screen was placed in relation to the robot, and also how the ultrasound probe was attached to the robot. And additionally, you can see the interaction technique where this virtual probe is moved to move the real probe. And also you can see the geometric shapes and the ultrasound images that the participants had to locate. So now here in the left column, we can see the visualizations at the screen. So in the top row, the bar, bottom of the arrow. Then now we can see the probe placement. So the visualization is in robot end effector at the probe. And then here on the right, we see the visualization in the field of view. And also here in the top, you can see relatively well this here the participants have to locate. Now we come to the results of our user study. So first, regarding the SensARy substitution modalities, we found that multimodal feedback was significantly slower than unimodal or no feedback, and vibrotactile feedback led to a higher force deviation compared to visual and multimodal feedback. You can see that in the blue left plot. Additionally, we found that the subjective measures showed improvement with all feedback approaches. However, multimodal and visual feedback achieved even better perceived difficulty than vibrotactile feedback alone. Regarding the feedback design, we found a significantly lower average absolute force deviation for the bar compared to the arrow. And according to participant feedback, this may be due to the gradual color changes and the disappearance of the error that made it harder to accurately perceive the force changes. For the visual feedback placement, we found a significantly lower perceived difficulty for the screen placement compared to the probe placement, and we found the screen placement led to a higher perceived continuity of force perception than the other two placements. And the participants attributed this to their focus being primarily on the ultrasound image, and that the world stabilized placements were less confusing than the body stabilized ones. We also found one interaction effect that you can see on the plot here. Here it is noticeable that without vibrotactile feedback, so on the left, the screen placement for the bar performed worse than the other combinations. However, when vibrotactile feedback is present, so in the right, you can see that the bar on the screens performs better than the others. So this aligns with participant feedback, where they said that the vibrotactile feedback was used as an alert, so it guided the attention towards the visualization when the force got too high. While we had some interesting findings into modalities, feedback design, and feedback placement, there are some limitations that have to be considered. So firstly, we only used one type of vibrotactile feedback. Future work should assess the potential of other scaling approaches, so other vibration patterns, and also the use of vibrotactile feedback as an alert. Another limitation arises from the expensive optical see-through displays we used. This limits the broad applicability. However, we saw that the screen placement was beneficial, so this could also be realized more cost efficiently, and this should be explored in the future. The last limitation comes from our study focus. So we investigated SensARy substitution approaches for one specific task, so for robotic ultrasound. However, the force perception, as I said in the beginning, is also crucial for industrial and surgical tasks. We believe that with other scaling approaches and task-specific placement, our results might be transferable, but however, of course, this should be further evaluated in the future. So this brings us to our conclusion. So we found that regarding modalities, the presence of visual feedback is crucial. However, the vibrotactile feedback can be a meaningful addition if it's used as an alert. Regarding the feedback design, our results indicate that a color and height changing bar is more suitable for precise force perception than an arrow. And finally, regarding the visualization placement, the visualization should be anchored in the environment close to task-relevant locations, which in our case is near the sonographic image. With that, I want to thank you for your attention, and if you have any questions, feel free to reach out to me.